do this. All right, looking at, this is an example of a table R, right, that you had in your notes, in your lab, okay? So can anybody tell me any observations that you had about these two columns? Peter, what do you got?
The negative directions end up with negative velocities.
Very good. The negative directions, you had negative velocities and also negative slopes, yeah?
Mm-hmm.
Awesome. Great observation. What else? Lauren?
The slopes and the instantaneous velocity are basically the same.
Oh my God. The slopes and the instantaneous velocity are basically the same. That's huge. That's literally like the big idea here, okay? And that's what we're going to be working on today, all right? What are the units for the slope? And how would we get them? What do you think? Rocco?
Well, isn't it mean? Is it position over time? So it's going to be mean.
I'm just right here.
Okay. Hi, Cons. Okay, yes. So the slope that you're calculating, all right, let me see. Do you guys see that well? Is that good? The slope is rise over run, right? And the rise is a change in what? Position, because that's what is happening on our y-axis, right? You can look here. There's our rise. And there's our run. So our rise was a change in position. And what was our run? A change in time. Very good. A change in time. So what are the units of position? Meters. And what are the units of time? Seconds. There you go. Those are our units for the slope. Does that make sense? Yeah? Anyone? Good morning? Hello? Okay. So, rise over run is what we're going to keep talking about. So, what is the connection between the slope of the position time graph and the velocity data? What do you think, guys? Good morning. Don't make me feel like this is virtual, guys.
I'm sorry, I don't
Talk to me. You don't know?
know.
Does anybody have a guess of how this column compares to this column? How they're related?
Well, I mean, they're both the change in seconds.
Okay.
Both represent the change.
They do. And Daniel?
Because slope is velocity.
Yes, it's the same. That's it, guys. The slope of the position versus time graph equals the velocity. And I left a blank there because we've used lots of words in front of velocity before. What words have we used?
Instantaneous.
We used instantaneous. What else? Initial. Shout them out, people. Final, average, good. In this case, it's going to be instantaneous. Oh my goodness, that's not even. Let's try that again. I have many good qualities, but my handwriting is not one of them. So I'm sorry if I write something and you can't read it. Instantaneous. So the instantaneous velocity is that slope of the position time graph. Now, when we were looking at our constant velocity situation, it kind of didn't matter where on here you measured the slope, right? Because the slope was the same the whole time. Does that make sense? And so that's the really important thing here, is that constant velocity is the same slope the whole time. And that's what a line is, right? A line is just the same slope. But if you have something accelerating, right, then it might look like this, where the slope is changing, okay? And that's what we're going to talk about next time. Okay. How are you feeling about this?
Okay.
Is okay? Questions? Confusions? Confusions. That's a word now. Okay? Okay. So that's the really big idea here, is that the slope of the position versus time graph is your instantaneous velocity. So now let's think about, what about these big pushes versus the small pushes? What were some of your observations about those?
It's really hard to do them.
It was hard to do them? Okay. What else? Was there any difference? Jordan?
The big push, it went like faster, and the small push, it was slower.
Yes, sir. The big push went faster, and the small push went slower, right? And we can see that here, right? 1.686 is less than 2.13. What do you think about this one? Why is that one a little weird? Yeah, Brandon, the 3 and 4.
It's because it's closer to a positive number because you're going slower in the negative direction.
Wow, yeah. So that negative is that direction, right? But when we talk about fast or slow, we're talking about the speed only. We're talking about that absolute value of that number. So 2.23 is a bigger number than 0.945. That negative just was indicating the direction. Do you see the difference there? Okay, sweet. So big push versus small push. All right, so the big push was faster and the small push was slower. What did the lines look like? How did the lines compare if you looked at them? Which one's steeper? Faster. Exactly. I'm going to change colors here. Okay. So steeper and shallower. Let's see if we can make sense of that, okay? When we think about steepness or shallowness, we're talking about slope, right? So we're talking about rise over run. So let's say I took the same run, okay? And that run is my delta t, right? That's my time. That's the change in time. Yes, vigorous nods. Look at my rise. My rise is my delta x. And in my faster one, my delta x is bigger for the same amount of time. Take a moment and think about that, right? And this is where you're like, wow, I'm glad I came to high school, so you can say that people travel further in the same amount of time if they're going faster. Yes, right? That's something that like you get, right? But what I want you to bring together is this idea of slope, right? And that rate of change and how those all go together. Does that make sense? How are you guys doing? Sort of? Where did I lose you? The deltas. Okay. Remember, deltas change, right? So I'm looking at this point versus this point, right? These 2 points. And I went a certain distance, right? From here to here, and then in a certain amount of time. And so I'm comparing how far did I go, that distance, in that amount of time. Okay? Awesome. So for the same time, the steeper one, which is faster, goes further. All right, how's that feel? Okay. It's weird doing this recording because I'm used to walking around, but I'm trying to stay close so that it picks up my language, because I'm trying to make sure that the people who stay at home also have a way of getting the notes. So I thought this would work. Okay, you guys still writing? Okay, cool. I'll give it a second. I'll even pause. Okay, so if we look at this, it's like an example of a good trial, right? And what we're looking at, again, is that rise over run. And so what I'm hoping you realize is that delta x over delta t equals v is something that we've used before, right? That should be familiar. Is it familiar? Or is that the first time you put it together? Which is fine, right? But those are now coming together. So again, the change in position, how far, delta x, and the change in time, delta t, right? How long, right? That comparison is how we get those velocities. All right? So let's actually calculate and look at delta t's and then delta x's and see what happens. Let me pick this color. Okay. So I go from 2 seconds to 2.5 seconds. What is the delta t there? 0.5 seconds, right? I'm going to make this a little bit bigger. All right. What about from 2.5 to 3? Everyone now. 0.5 seconds. All right. 3 to 3.5. 0.5 seconds. All right. So there we go. So I've picked some data here so that you can see equal time intervals. And we have some data saying, okay, it was at 3.5 meters when the timer said 2 seconds, right? So all that stuff. So now let's calculate the corresponding delta x's. Ooh, who's really good at mental math? Or you have a calculator. What is the delta x for this one?
86.
86 hundredths, sure. Good. 0.86 meters. What about the next one? It is 86 again. All right, what about this one?
Is it 86?
No.
Yeah, it is.
No, it's not.
It's
82.
It's 82. And what's this one? 80. Why? Why do you think it went down a little bit?
Because it started getting slower.
It started getting slower. So if it started getting slower, then it started traveling less distance in each time. Is that making sense, how it's getting together there? Okay, awesome. Now we could even make sure that these numbers are right? Grab one of these delta x's and delta t's, right? So 0.86 meters divided by 0.5 seconds, and that is 1.72 meters per second. So that's pretty close, right? And remember, we're just sort of we're dealing with some rough numbers here, okay? But hopefully you can see how that just raw data of position and time, how that can be turned into that delta x and delta t, right? Because each one of these points is a moment in time. Those are all instantaneous positions, instantaneous times. Does that make sense? Nice. All right, we're almost there, guys. So I want you to look, I've color coordinated these. So I want you to look at this real quick. You see the yellow 3.5 and the red 4.36? So I took a little sort of meter stick, but it's like a 10-meter stick, I guess, and put the position, right, sort of trying to color coordinate where the position goes. And so you can see how it kind of looks over time with equal time intervals. Does that picture kind of make sense, what you're looking at? So tell me what you see in that picture. Yeah, Maya?
The dots get closer together.
Yeah, okay. So this and this, like honestly, those are the same-ish, right? This is pretty close. These are all pretty close. This one's maybe a little bit smaller, okay? But again, that's what we're saying. It's getting a little bit slower. But if you just looked at that, it looks pretty close to constant velocity, right? It's covering basically the same amount of distance in little chunks of time, right? So what I want you to see, this is called a motion graph, and we're going to be looking at those more when we think about when things accelerate. Okay, so it's important to understand what you're looking at so that when we do something a little bit more complicated, that you can bring it together. All right, questions?